So, hello everyone. This is joint work with Przemek Uznański, who is somewhere in Marseille. I'm not sure how to pronounce the name of his university, so sorry for that. It's about some version of pattern matching, order preserving pattern matching. And I'm sure all of you have done something with pattern matching, at least once or maybe twice. I see a few people who have done something with order preserving pattern matching. Still, it's a different version of order preserving pattern matching. But first, I should define what is the usual order preserving pattern matching. So the idea is that, as usually, I mean, you get some long text, you get pattern which is long or maybe short, or you want to find a fragment of the text, which is, in this case, order isomorphic to the pattern. So what does it mean that something is order isomorphic? So we say that two sequences of numbers, so we are working with sequences of numbers, are order isomorphic when the sorting permutations of those two sequences are the same. So for example, you can see that 4 to 1 to 3 is order isomorphic to 63, 12, 23, and 42 because the smallest element is at the second position, the second smallest element is at the third position, then the next element is at the last position, and the largest element is at the first position, right? So they're essentially the same. So now order preserving pattern matching is simply that you are given a text of length n and a pattern of length m, and you would like to find a fragment of the text of length m, which is order isomorphic to your pattern. So essentially the same. So this is kind of related to something known as permutation patterns, where you look at subsequences of the text. But it turns out to be quite different problems. But still, I wanted to mention that it's kind of similar flavor. So there have been quite a few papers on the order preserving pattern matching last year and this year. So what's the message from those papers? Well, the message, as far as I understand, is that the problem can be solved in close to linear time. So you need to sort something, and that's it. The rest is linear time. So for order preserving pattern matching, we understand the problem, right? So what should be the next step? Well, you could move to something completely different, or you could try to make this problem slightly more complicated. So what could be this complication? Well, maybe you should move to approximate variant of the problem. So maybe you should relax the notion of matching a little bit. So maybe you would like to find a fragment of your text which is almost order isomorphic to your pattern, so almost the same. So now the question is, what should the almost mean? I mean, you can have multiple ideas how to formalize that. And when you think about the usual pattern matching, which you all know, there are at least two natural definitions of what this almost could mean. And one of them is pattern matching with k mismatches, and the other is pattern matching with k errors, so mismatches or errors. Okay, so we thought about it a little bit, and we tried to find some definition which kind of works for the order preserving pattern matching, where we can still do something interesting algorithmically. And it turned out that with errors, I mean, we didn't know what to do, but we could do something for k mismatches. So first, I should define what I mean by mismatches in this context, because it might be not clear. So first, I should define what does it mean that two sequences of numbers match with up to k mismatches in order preserving sense. So I mean by that I can choose up to k indices, A1, A2, and so on, and then I remove the numbers at those positions from both sequences, so the same positions in both sequences, so I get two shorter sequences. And I would like those shorter sequences to be order isomorphic. So if I can choose those indices, those positions which I remove from both of them at the same positions in both of them, and if I can get order isomorphic things, then I'm saying that the original sequences are order isomorphic with k mismatches. So just as short example, so you can see that those two sequences are not order isomorphic, but when you remove 5 and 7, so there are the same positions in both sequences, so second to last position, you remove them, and you get something which is order isomorphic. So it means that the original sequences were order isomorphic with one mismatch, which we denote with this one here. So, okay, so I'm calling that order preserving pattern matching with k mismatches, and from this definition, it might be not clear why I'm talking about mismatches. Maybe I should be talking about omissions or something similar. So you can see that the definition is actually equivalent to a different definition, which is in red, which is that you choose k indices, but only in the first sequence, and you are allowed to modify the elements, the numbers at those k positions. and you would like to modify them in such a way that you get two equivalent sequences. So in this example, you can take 5 and change it to 3, and you get 2 sequences which are order isomorphic. And those definitions are equivalent. And here, I mean, maybe it's more clear that why I'm talking about mismatches, because essentially I want to choose k things and change them. So it's a little bit like mismatches, talking about mismatches. OK, so that's the definition. And now I would like to solve order prismatic pattern matching with k mismatches, where I also get text and the pattern and the number k, and I want to find all the fragments of length m of the pattern such that the corresponding things are matching up to k mismatches. So that's my problem that I would like to solve. Yeah, so you can see some small example, and you can find one match. So I will make one assumption for the talk, that the numbers in the sequences, so in the text and the pattern, don't repeat. So we remove the assumption in the paper, but it makes life more complicated. So now everything is unique. So the first step should be that we need some way of checking whether two things are order isomorphic with k mismatches. So even without talking about pattern matching thing, you just want to check whether two things match to each other. So the question is whether you can do so. And when you think about it, it's not difficult, but maybe not completely trivial. But you can see that two sequences are isomorphic with k mismatches when you can choose m minus k indices such that the corresponding numbers in the first sequence are increasing, and also the corresponding numbers in the second sequence are increasing. So when you think about the division, you get the lemma in a straightforward manner. OK, so we get some lemma, and now how to do this lemma, because so far it's not efficient. So it turns out you can do the following simple thing, which I will show you an example. So let's say that you want to check whether those two sequences are order isomorphic with 3 mismatches. So you look at them a little bit, maybe it's not clear whether they are or they are not. You can do the following thing. First, you find the sorting permutation for the second sequence, and you apply the sorting permutation to both of them at the same time. And you can see that that doesn't break the fact that they are the same or they're not the same. So applying the same permutation to both of them. So I apply the permutation, and now the second sequence is increasing, right, because it was sorting permutation, and the first thing is, well, something. And now the thing is, when you look at the previous simple lemma, you can see that because the second sequence is increasing, you are really looking at an increasing subsequence of the first sequence. So now you only need to check whether the first sequence has an increasing subsequence of length m minus k. And that's like a standard exercise to check whether a sequence contains a long increasing subsequence or not. So you think about it, and you see that there is indeed such a subsequence which is marked in red. It's increasing in the first sequence. And from that, you get that the original sequences were order isomorphic with 3 mismatches, because you lose those 3 non-red guys, and that's it. So the only thing I did was sorting the second sequence and then finding longest increasing subsequence of something. So those are things you can do efficiently. So depending on your model of computation that you like, it's either m log m or maybe m log m if you like Van M debaucheries and things like that. But anyway, it's close to linear. So that's easy. Checking whether two things are matching with k mismatches is easy. OK, but we wanted to solve pattern matching, right? So we get multiple possible windows of length m, and for each of them, we would like to check whether the corresponding fragment matches the pattern or not. So of course, you could take the previous, this simple algorithm and apply it to every window of length m separately, right? But then your complexity is n times the time for this check, n times m, and that's kind of boring answer, because you are doing something separately for each possible window. You are not using any correlation between them. So the usual assumption in approximate pattern matching is that the k, the bound on the number of errors, is small. So you allow like 7 mismatches or 7 errors. And you would like your algorithm to be faster as you decrease k. So for k equals 0, you want something very close to linear. For k equal 1, you want something slightly slower, and so on and so on. So we would like to get a complexity which is n times f of k, where f of k is some function, hopefully slowly growing function, but just some function. So this is not such a complexity, right? Because we have n and m. So what you could do? Well, you can use the following plan of the attack. So you move your window of length m over the text, right? Well, maybe from left to right, right? So it's like that. And for every possible alignment, so for every possible occurrence, you do one of the two things. The first thing is that you somehow very quickly detect that this window cannot correspond to an occurrence, because the number of mismatches must be larger than k. And you use some very quick and simple test to do that. So that's one possibility. And if your test tells you that, I'm not sure, then you do some more clever and time-consuming check to verify whether indeed the order-preserving distance is at most k or not. So that's plan of the attack. Okay, make some sense? So this was used in the usual approximate pattern matching. I'm not sure what was the first paper, maybe Cole and Hariharan, where they did something similar, and it was also used by Moshe, I guess, in a parameterized approximate pattern matching, and maybe also somewhere else. So the plan of the attack is kind of standard by now, but how you implement those two things differ, right? Because the problems are different. So it turns out that so we need this quick and dirty check, which will allow us to quickly eliminate lots of starting positions. And it turns out that for that, it's helpful to introduce a notion of signatures. So signatures were also used in order-preserving pattern matching without the mismatches, but they were slightly different, so I will show you the difference. So a signature is something which you compute for a sequence, and it should capture some of this order structure, but just some of the structure, so that when you move the window, you can update those signatures efficiently without recomputing them from scratch. And it turns out that the following definition makes sense. Maybe don't look at the definition, look at the example. You have some sequence, 11, 4, and so on, and the signature is something like that because of the following reason. For example, you look at 7, and you find its predecessor in the sequence. It's 6, and it's 5 positions to the right. Okay, so you output 5 in the signature. So the 5 describes 7 in the signature. And you do that for every possible element of your sequence. So you output the distance to the predecessor in the sequence. And that's the signature. Okay? So now you can prove two nice properties of those signatures. The first property is that when you have two sequences which are order isomorphic with k mismatches, then the Hamming distance between the signatures is at most 3k. So not k, but 3k. You lose a little bit, but a little bit. And you prove that by induction on k, and I will skip that, but I will show you an example. You can see some two sequences. Their order isomorphic with 2 mismatches, but because you can remove those 2 red things, and the signatures, you have to trust me that the signatures look like that, and the Hamming distance between them is 6, so the lemma holds in this simple case. So it's a very local property. The signatures are local property because they depend on element and the predecessor. So that's the reason for the lemma, essentially. So that's the first property. So what's the second property? So recall that we want to move a window of length m over the text. And we would like to maintain the signature of this fragment of the text as you move the window. But we would like to do that efficiently. So we have to think a little bit how the signature changes when you move the window by 1. And the thing is, we output the distances, not the absolute positions. And that's the reason why the signature doesn't change much, because the distance stays the same for most of the elements, except for the element which disappears from the window. And you have one element which appears, one new element. So for those two things, you have to change something in the signature, but for the remaining elements, essentially, you don't have to do anything. So the signatures, when you move the window by 1, change at constant number of positions. And you can actually find out which positions are changed in some small complexity, logarithmic complexity. So you keep some predecessors, successors, and that gives you what you should be changed. So that's how the signatures change, so that's good. So we maintain those signatures as we move the window. And now we compute the Hamming distance between the current signature of the fragment and the signature of the pattern, which we compute in the very beginning. If the Hamming distance is at least 3k, you cannot have a match because of this lemma, which I haven't proven. So you just continue to the next window. If the Hamming distance is at most 3k, you don't know. Maybe the actual distance is 3k minus 1k. You have to do some additional check. Okay, so that's one thing. But how do you do this check whether the Hamming distance between the signature and the signature of the pattern is at most 3k? So it turns out that this is kind of standard thing if you have suffix arrays, some LCP queries, and the kangaroo jumping, which was mentioned already. So the only difference is that now the signature of the fragment changes, so you have to be more dynamic, and that's kind of straightforward exercise. So you can maintain the signature and compute the Hamming distance in time O of k, essentially. So that's one thing. So in some cases, you are done, because the Hamming distance is too large, and you can continue. But in some cases, the Hamming distance is at most 3k, And now you have figured out whether the actual fragment and the pattern are order isomorphic with k mismatches or not. And you need to do that in time depending not on m, which is the length of the fragments, but on k, which is the bound on the number of errors. So you would like to do that. And how you can do that? Well, it turns out that you can reduce that to a generalization of the longest increasing subsequence, which we call heaviest increasing subsequence. So as you can guess, it's just the elements have weights, and you are looking for a subsequence with the largest weight. And that's the only difference. You can solve the problem in almost the same complexity as the longest increasing subsequence using the same methods, some binary search or balanced search trees. And how the reduction works. So the intuition is that if the signatures of two sequences agree on most positions, then checking whether their order isomorphic is kind of easy if k is small. And more formally, you can prove that the following statement. So if you are given the L positions where the signature differ, so those are places where the signatures are different, then you can reduce in time L times something small, checking whether those signatures match with k mismatches or not, to computing the heaviest increasing subsequence on L+1 elements. So if you can do that, then the reduction works in time L, which in our case is at most 3k. And this is, again, L+1, so 3k plus 1. So you will get a test which works in time O of k times some small logarithmic factors. But why the lemma holds? I mean, first of all, you need to do some preprocessing to apply the lemma. So you need to store some things like the sorting permutation of your pattern and the ranks of elements, so that you do just once. And then you apply the lemma for every window. And the intuition behind the lemma is that recall that we had this very simple observation or simple lemma that what you really want to do is to find whether you can choose m minus k positions in the sequences so that the corresponding elements are increasing in both of them. Okay, so that's what we want to check. And now the thing is, if you have the ith characters of both signatures, which are the same, it means that their predecessors are at the same positions in both sequences. So you have some element, I don't know, 17 and 29 in both sequences, and the predecessors are at the same position, like 7 positions to the left or to the right. So now it turns out that either you should take both the position, so let's say that you have position I, and the predecessors are at the same positions j in both sequences. So then it turns out that you should either take both I and j as your indices, those indices, or you shouldn't take any of them. So in other sense, you don't have to think about those both indices separately. Either you take both of them or none of them. So then when you generalize this simple observation, I mean, you have to, of course, prove it and so on, it turns out that the only places where you have to make some decision are the places where the signatures are different. Because in other places, you kind of continue the previous decision, so to say. So when you have just L positions where the signature is different, then you have just L places where you should make some decision, and additionally you have the position where the predecessor is not in the sequence, the smallest number. So you have L+1 things where some decisions should be made. And the decision is actually the same as the decisions that you make in the heaviest increasing subsequence, which is take or not. So that's how you reduce it to the heaviest increasing subsequence, assuming some preprocessing, because you need to jump between those guys efficiently. Okay, so then you combine all those ingredients, which I tried to sketch, and you get that for every possible window, your time complexity is some logarithmic things to maintain the signature, and then k times some logarithmic things because you need to find the heaviest increasing subsequence. So, and you also need to compute the Hamming distance, but that's plus k, so that's kind of hidden there. So then you can, with some standard tricks, you can replace n by m here, and you get the final complexity, which is n times log log m plus k log log k. So if you don't like Van Emden-Bos trees, then just replace log log by log in this complexity, because that's the only reason we have log log instead of log. Okay, so that's the result. And now there are two questions that maybe you will like, maybe not. So first thing is that we tried to think both about errors and mismatches. We couldn't find a definition of pattern matching, order preserving pattern matching with errors, where we could do something polynomial. So maybe you could come up with some definition. So or maybe you could get an algorithm with time complexity n times f of k, where f is not polynomial. I don't know, but maybe you can find some definition where you can do something interesting. And the second question is that for the usual pattern matching, there was at least one result by Amihud and Moshe and Eli, where they got n times square root of k times something. I don't remember what was. You should ask them. So the question, they use some pigeonhole reasoning and more combinatorial insight. We don't see whether you can do this here. I mean, the same thing doesn't work, but it's not very far away. So maybe you can generalize what they were doing. That would be interesting, I think. So whether you can beat n times k for the problem. OK, so that's all, and thanks for the attention.
Any questions?
There are several definitions of signatures for this problem.
Mm-hmm.
Have you tried to use some other?
So the first thing, in our case, it's very important that we output the distance to the predecessor. In all the previous ones, the result was the absolute position, the offset in the sequence, and that's the crucial change. Otherwise, the two definitions were the position of the predecessor, either in the whole thing or in the prefix. So I think if we look at the prefixes, I don't think it would work. So we need to look at the whole thing. So those are the two definitions I have seen. So essentially, the only change in our case is that we output the distance, the relative thing, and that's really, I mean, it's the same thing, but we need to update it efficiently. So it's essentially the same idea for the signature, but we output the relative offset instead of absolute offset.
Any other questions? Okay, thanks again, Pawel.